Introduction. This talk is put together by some of my amazing colleagues listed here, and I'm just sort of distributing the knowledge. So a bit about myself. I've been working in security since 2011, held various roles at various companies, and I've been in the blockchain smart contract auditing scene since 2018, and it's been a hell of a ride. Who I work for Quantstamp, which is the company, the logo there in the middle. We're one of the leaders in smart contract and blockchain security. We've secured more than 200 billion in assets in smart contracts. We have a lot of clients, a lot of revenue, and most importantly, we're hiring. So stick around until my last slide. That one has a very interesting piece of information on it. So why is this talk relevant? There's been a bunch of bridge hacks over the past year. So just in 2022 alone, there's been more than 1 billion worth of crypto assets stolen from such systems. Here I list just a few of them, the ones which are like most important. And we're going to go through more details as to why these kind of things happen and why this kind of thing is so hard to get right from a security perspective. So here's a bridge. It's pretty simple. Like you'd say, like, why the heck is this thing so hard to get right? You have an actor on the left side. You have a smart contract system like Ethereum that it interacts with, and it basically wants to send assets to a different chain. And on the other end, this actor or someone else might want to receive those assets denominated in something else on the other chain. Now, this is like the essence of it. Going into a bit more detail, you see like when someone deposits, like this actor on the left, deposits maybe some ether, it interacts with a smart contract called a custodian, and there's a communicator in the middle, which is an off-chain component. It could be a traditional whatever server application that is watching what is happening on the chain. Once it sees that someone has deposited funds in this contract, it initiates a debt issuance call to the debt issuer contract on a different chain. And this debt issuer here on the right-hand side, it mints some tokens, which should be the equivalent of the ether that the first actor put in, right? So again, pretty simple. The opposite path, so starting from right to left, the actor wants to redeem back the ether deposited after having used it for some purpose. So it burns these tokens that it got called ACETH. It sends them to this debt issuer contract. The communicator is also watching the debt issuer. And when it sees that someone has burned these tokens, it initiates the fund release on the custodian side. So the actor should receive the corresponding amount of ETH on the Ethereum side. So this is depositing and withdrawing. Now, you notice from the previous slides, the bridge structure contains like 3 main components, 2 contracts, which are the asset custodian, the data source, and the debt issuer, Oracle contract here, and a communicator, which is an offline, off-chain component, which we call the Oracle. And there's therefore a huge attack surface when it comes to like the Web3 space. So you have the custodian, the debt issuer, the communicator, any interfaces that they use, and the network itself. They could all be subject to attacks. And in the next slides, we're going to go through examples of attacks for each of these layers. And bear in mind that some of these attacks, I won't name names because it's not professional, but some of them are referring to the hacks that happened in the past, the ones that are on the one of the previous slides. So for the custodian, we have something which is called the call relay attack. And here, depending on the bridge, you might have this asset custody smart contract, which is accessible by some privileged addresses because they need to manage them somehow and maybe maximize the profit of the project or something. So what the attacker goal in this case was to take over this asset custody contract and be able to take funds out of it. So the way in which they did that was that there was this function that was in the asset custody smart contract called change custody address. There at the arrow at the bottom. And this function should not be callable from the outside. So there should be some access control in place that prevents anyone from calling it. But what the attack, or like what any user would be allowed to do, was that they were allowed to call functions of this form, right? There was a function name, 3 parameters, 2 byte strings, and 1 unsigned integer on 64 bits. So this was something that was deemed allowable from the access control policy because there were just 1 or 2 functions which were fine to be called by anyone. Now, the nasty part is that the attacker found a hash collision on some random name that they put together using this signature here. So they just randomly compiled a function name and some parameter values which had a hash collision with this function name. The way in which this contract in the middle here works, this cross-chain communication contract, whenever it says call this function, it basically hashes the signature and looks it up in a hash table. And due to this hash collision, the attacker was able to figure out, okay, if I have this function, well, it's just a random name there, but XX123, and some parameter values is going to have a hash collision, and I'm going to be able to call this function, which I'm not supposed to call, and change the owner of the asset custody to my own address, and then I can just take the funds out. So yeah, that's one of the attacks. Moving on to another attack, transaction replay. It's again on the custodian, and depending on, again, the custodian, the bridge that is implementing, you need to present proofs when withdrawing assets. So these kind of Merkle proofs, they get issued. So let's go step by step. The first step is that you deposit an asset to the custodian. And in the second step, the debt issuer sends you the debt token. We've seen that on the original slide with depositing. Then withdrawing, you do burning the debt token to the debt issuer. And in this case, the debt issuer gives you a proof that you can then go and send to the custodian and say, here's the proof, give me my money, give me my tokens. The mistake in this case was that the verification of the proof didn't take into account one of the fields. So the attacker was able to change one of the fields and resend the proof again and again. It was a valid proof, but it was different from the previous ones. So for each replay, the attacker got the same amount until it drained the custodian. Going on to the debt issuer. So in case of the debt issuer, the attacker goal would be to bypass the signature verification, right? And arbitrarily mint these tokens, right? So the attacker, what they did in this case, it was again a very specific implementation of a bridge which received as an input parameter over here, I'm not sure if you see my mouse, oh, yeah. It received the signature verification contract address, right? So this was an input parameter, but it should have been pretty fixed. But this is the way in which the system worked. They were just receiving this as an input parameter, and of course this signature verification contract was unique. It was a trusted component. What the attacker did, they deployed a fake verification contract, and they passed that as an input parameter. So this fake verification contract said, it's always good. Whatever you do, you passed the signature verification. And this way, the attacker was able to basically initiate these kind of withdrawals without, or like this minting without deposits, without actually depositing any money in the custodian. Moving on to the communicator layer. There, the attacker has the goal of tricking the communicator into forwarding invalid messages and minting tokens. So for this particular attack, the communicator was watching the custodian and was watching if someone deposits funds in the custodian, there's an event which is emitted. I'm going to check how much I should emit. I'm going to check the address of the custodian is correct. Unfortunately, for multiple withdrawals, it was looking only at the first event for the address of the contract which emitted it. What an attacker did was they deployed a malicious contract which emits the same events. The events look the same except for the fact that it's emitted by a different address. The problem with the communicator, it was only checking the address of the first event and then only looking for the other events that came afterwards. So the attacker basically issued a bunch of fake events from this malicious contract and was able to basically get a bunch of funds that they were not entitled to. Moving on to the interface level. Here, there's a bunch of attacks which we're going to look on. The first is you have this situation where a legitimate user here at the bottom has approved a contract to allow them to basically execute some kind of function call for a particular token. And this is quite broad. So what an attacker did there was that they just crafted out of this execute call data generic function, they just crafted, okay, transfer from user to me, right? So they were able just to easily craft this function call inside of the call data, which led to all of the legitimate users' tokens being transferred to the attacker. So the attacker could do this for multiple users who have approved their wallet, this interface spending money from or funds from their wallet. In a similar attack, where again the user has approved a third-party contract for allowing people to deposit with permission, basically here you're allowing someone to spend money in your name, it should only be meant for tokens which implement this feature. But there are tokens which do not implement this feature and do not give any warning as to the fact that this function call failed. So if someone calls this function deposit with permit into this contract, it's just not going to say anything. It's not going to return anything. And the error was in this third-party contract where they did not check the return value. So they didn't check that the return value is explicitly successful. They just assumed that if it doesn't complain, then it's successful, right? So missing return value validation. And this way, the attacker was just able to say like, hey, I'm going to deposit all of these funds from the legitimate user into my account. And that's how they got away with all the funds from legitimate users who approved. Finally, the network layer. This is something that hasn't yet happened, but might happen in the future. There is this thing called the 51% attack, which allows you to reorganize blocks. And what you can do is launch such an attack on a level 1 chain. Then you deposit assets to that custodian contract, and you receive the DEP token. Afterwards, you take that DEP token and withdraw those funds out of an exchange or something. You withdraw them, transform them into fiat or dollars or whatever. And finally, you cancel that deposit transaction in step 2 because you now can reorganize the chain, right? And depending on how long these steps, this withdrawal process takes, you could afford to pay for such an attack because 1 hour of such a 51% attack on the Ethereum mainnet is somewhere between 1.5 and 2 million. If there are sufficient funds, an attacker might be incentivized to actually pay this for a certain amount of hours, depending on how fast the bridge enables someone to transfer funds, to deposit and withdraw. So in summary, there's a lot of bad things that could happen with bridges. We saw things on the custodian layer. We saw things on the debt issuer layer. I'm not going to go into all of these, but basically, you might have recognized that these are not totally different from your classical security mistakes, like missing input validation, not checking return values, and so on, right? The communicator layer is this off-chain component, which is basically watching and triggering smart contracts on both sides. And there's many things that could go wrong. We only went into one or two things in this presentation, but there's a longer list, and probably it's not exhaustive. There's the interface, where basically it's not necessarily bridge specific, but there's a lot of things that could go wrong with allowing people to deposit in someone else's name or allowing external contract calls. And then finally, the network layer, there's the 51% attack, but there could be other problems as well. Finally, just want to say we're hiring, we offer great packages, and if you're interested in this kind of stuff, finding bugs in smart contracts, we'd be happy to get in touch with you. Thanks so much.
So, do we have any questions for Sebastian? That we have a runner who's coming forward.
So it looks like a lot of stuff you mentioned is, like you said, input validation, stuff like that, that could be remediated with like good programming practices. Is my assumption correct that if you do all these correct, then the problem is the custodian, and there's no way to do that one trustless because it is off-chain. So can we ever get rid of, not the communicator, because that is off-chain. Is there ever a way to make that component trustless as well? Or will that always be a linchpin in the entire setup? And there's no way to secure it even if all the rest is perfect?
Yeah, that's a very good question. Thanks. So this architecture, which we've mainly looked at during this talk, is something which is being used generally right now. There are projects out there which are taking a totally different approach. They don't use this architecture. They use something else where they don't have this kind of trusted off-chain component. And well, those kind of things are not yet in production, but they are working towards a solution which does not have this kind of trusted third party which is off-chain.
Okay.
If you want, I can give you more details
Sure.
in the break.
And another question, if I may.
Sure.
For example, in terms of web applications, we have stuff like Portswigger Academy. Do you have equivalents for, like, if you want to learn about smart contract blockchain? Is there any like playgrounds that are easy to get into for someone that is not familiar yet? Totally.
Yeah, there are multiple actually. There's things like, well, I'll call them offline CTFs because they are always going on, right? You just have like a playground where there are some contracts that you can just exploit, toy contracts. And there's like multiple difficulty challenges, right? And there's like things like, you know, damn vulnerable Linux?
Sure, yeah.
There's something like that for smart contracts. Or
so just Google damn vulnerable Ethereum or?
Yeah, damn vulnerable DeFi it's called, yeah.
Okay, yeah.
So there's all of these kind of things. And also there are training programs free of charge because there's so much interest in getting more security experts in this field that people are no longer charging for training. Everything is sponsored by all these projects which have suffered such hacks, and like the amount that they need to sponsor these academies is nothing compared to the amount that they could lose. So everything is like sort of free of charge, so you can pick it up really easily.
Okay, thanks.
Thank you.
Please come up with your question.
Hello. For someone that is completely new to this type of hacking, I have a question. How much of hacking smart contracts and blockchain and cryptos is about actually cryptography, and how much is about more of this type of logic books?
That's a good question. I think probably more than 95% is about this.
Okay.
And probably like 5% is about the crypto, because the actual cryptography which is being used, that is being actively researched by many research groups at top universities and many of the world's leading cryptographers. So the actual hash functions, encryption, proofs, and so on, everything is based on many, many years of research from universities. And now we're just like working at implementing applications on top of that.
Okay, so we can say something like, if you invest more time learning about Solidity, you are doing a very better investment than by learning, I don't know, cryptology, something like that.
Depends, right? If you're a brilliant cryptographer and you might invent something amazing,
I'm not.
then it might be worth doing that. But I think like if you don't want to do that, then definitely learning something like the Solidity or other programming languages being used for smart contracts is a very good return on investment.
Okay, thank you.
Thank you.
Any other questions?
Yeah, so I have a bit of a controversial question. So your company is like doing these audits for the contracts. So you're making money by doing the audits and stuff. But like I've read this idea that it's something like a bit like a reverse bug bounty scheme, because in the end there's an incentive for you to keep like some kind of bug in the contract and then in a black hat form exploit it. So you know what I mean?
Yeah, I do, totally.
And so it gets philosophical and everything, but like you're part of the industry. And what is your thinking about this? How this could improve in a way where it's better for everyone? Like you auditors can do your job, others can do their job, and everybody can trust the thing in the end?
Yeah. No, that's a very good question. Thanks. So I think it's always this kind of trust issue when you're working with a security service provider. It's not specific to this space. It could be like when you're pen testing a web application, right? For any company, right? You might withhold some kind of attack that you can then use to exploit. Of course, like maybe in Web 2, the damage you do is not directly financial, but it's reputation damage or so on. But basically, the idea is that what we're doing, if we were doing that, if we would be withholding and exploiting, there would be a huge reputation damage to the company itself, and it would cease to exist, right? We are, well, in relative terms, a young company. Like we've been around for 5 years, and we have a reputation for being one of the best. So if you have like the longer your time span is, and just keep in mind, the oldest auditing companies in this space are like 5-6 years old. So there's no others which are like, have been around for longer doing this specific thing. There's companies who have pivoted from doing traditional security to smart contract audits, and they have been around for longer. They have a longer track record. But definitely this kind of track record and knowing that the company has been around for longer helps with this kind of trust issue. Because if, let's say, you somehow manage to trick someone in trusting you, and you do this kind of thing, you withhold an exploit, you exploit it, probably in a few months to a year, your company is no longer going to be trusted by anyone because your audits always get hacked. You know what I mean? So that's sort of, I think, the way to balance this.
Okay, any other questions? Okay, I have a curiosity question. So suppose I wanted to exchange a large sum of money, and I knew it was going to be a cross-blockchain kind of exchange. Should I just avoid that altogether, or what can I do as a consumer of this entire process?
Definitely get advice from professionals, and don't just do it sort of on your own, because there are way more problems, sort of attacks, economic attacks, that someone could use to do an arbitrage on something that you're doing, right? So if you're exchanging one token for another, you have a lot of parameters, which might be like the margin that you're willing to lose in the exchange. And if you don't properly set that margin, you might end up being arbitraged by, there's an army of bots out there just looking for these kind of opportunities. So definitely ask someone for these kind of settings, right? And then like, this is in addition to all the security issues that might be there, right? So I'm not saying there are definitely ways to do that. I've done, well, I didn't transfer large sums of money, but I've done that myself with no, let's say, issues afterwards, right? So it's possible, but you really need to be careful, because like we've just presented, let's say, I don't know, 6, 7 hacks, but keep in mind there are like dozens and dozens of bridges, and some of them have never been hacked. Yeah, exchanges on themselves are bridges as well. They're just a different type of bridge. They're not from chain to chain, they're from bank account to chain.
Super. Any other questions then? All right, thank you so much, Sebastian.
Thank you.